Good afternoon. We were studying the analysis of impulse turbine in our last class, and I like to do a little bit of recapitulation of that topic, and then we will proceed with the further analysis. An impulse turbine, basically there will be two important components. One is a nozzle and another is the impulse blading. So, if we see a schematic representation of the impulse turbine, it is something like this. There is a nozzle through which steam is flowing, and when the steam flows through this nozzle, there will be drop in pressure and there will be increase in velocity, and then this steam will pass through the blade passages of the impulse turbine. So, I have shown two rows. This is the row for the nozzle and this is the row for the impulse blading. So, this is a stationary row where number of nozzles will be there, and this is a row of moving blades where very large number of blades will be there, and that will be rotating as they are mounted over the turbine drum or turbine disc. The steam path will be something like this. Steam is entering here, it is going through the nozzle, moving through this blade passage and coming out like this. So, this could be one particular stage of an impulse turbine, and after this, the steam should go to the next stage of the impulse turbine. What could be the different stages, that we will see later on. Now, it is important to know how the pressure and velocity changes when steam is flowing through these rows of nozzles and blading of an impulse turbine. So, here steam is entering at a high pressure. As it passes through this nozzle, there will be fall in pressure. After that, it is passing through the blade passage. In impulse turbine, there is no change of pressure when the steam passes through the impulse blading. So, if I call this as P, this is the length direction L. So, the pressure change can be represented like this. For velocity, when the steam is entering the nozzle, it will have a very low velocity. Then, when it is passing through this nozzle, gradually the velocity will increase. There is a small gap between the nozzle row and the blade row. Here the velocity will remain constant. After that, when it is again passing through this blade passage, the velocity will fall and ultimately it will come out like this. So, we can call this as V 0, the velocity with which it is entering the nozzle. Then at the exit of the nozzle, it will have velocity is equal to V 1, and that means it is entering the blade passage with a velocity V 1, and when it is coming out of this blade passage, it will have a different velocity. Let us say the velocity is V 2. So, what we can say that the inlet velocity of steam to the blade is V 1 and exit velocity or outlet velocity of steam from this blade passage is V 2. And we have to remember one thing, that the blade passage is not a stationary passage, all the blades are moving. So, the velocity which I have denoted here, this is the absolute velocity of steam which is entering the blade passage and which is leaving the blade passage. So, this is one way of representing how the velocity is changing through the blade passage. There is another way of representation where we can see in a very clear cut manner how the velocity change is taking place in an impulse blading. So, here also we are representing the nozzle and the blade, but on a different plane. Let us say this is the nozzle through which steam is coming. So, this is the nozzle axis. So, this is the direction at which steam is coming out of the nozzle. So, this will be the absolute velocity of the steam coming out of the nozzle, and obviously, this is the absolute velocity of steam which is entering the blade passage, and this is represented as V1. Now, this direction this direction is the direction of rotation, and let us say the nozzle makes an angle alpha with the direction of rotation. So, we can say that absolute velocity of steam makes an angle alpha with the direction of rotation. Here this is the relative velocity of steam as it enters the blade passage. This is the blade passage. So, this angle is known as blade inlet angle, and this is denoted as beta 1. This component of velocity is the blade velocity due to rotation, and it is denoted as Vb. This Vb that is obtained simply from the RPM of the blade and the blade diameter. So, the steam, we can imagine that steam is entering the blade passage, it will glide over this blade and come out. So, if this is the Vr1 is the relative velocity of the incoming steam, Vr2 will be the relative velocity of the outgoing steam. So, one can observe one thing, that Vr1, that is tangential to the blade at the entry. That means, if the blade angle at the entry is beta 1, Vr1 also makes an angle beta 1 with the direction of rotation at the entry. Again, Vr2 is the relative velocity at the exit, and it is tangential with the blade at the exit. Then we will have same magnitude and direction for Vb, that is the velocity of the blade in the direction of rotation, and joining these two we will get the absolute velocity at the exit, that is B V2. So, this is beta 1 and this angle is beta 2. One is blade inlet angle and another is blade outlet angle. So, we have got another representation of different components of steam velocity when it enters the blade and when it goes out of the blade. So, this is basically a triangular representation. The top triangle is known as inlet velocity triangle, and the triangle at the bottom is known as the exit velocity triangle or outlet velocity triangle. Now, these two triangles can be superimposed over one another because they have got a common component, that is Vb, and if we do that, then other analysis will follow from that combined velocity diagram. So, the combined velocity diagram that can be drawn like this. let us say first let us draw the common velocity component V b. So, we will have the inlet velocity triangle like this. Well, this is our V 1, this is our V r 1 and this is V b. We will have beta 1 and this is alpha. Again let me repeat, beta 1 is the inlet velocity angle and alpha is known as the nozzle angle, and we can see from the geometry alpha is smaller compared to beta 1. Then we can draw the other velocity triangle, that means the exit velocity triangle. So, we will have something like this. This is V r 2, the relative velocity at the exit. This angle is beta 2. This is V b and this is V 2, absolute velocity at exit. Another angle has to be defined. So, let us say this angle and let us give a name delta. So, now we can define a few more things. Let us do that. So, if I project vertical lines from the apex of these two velocity triangle and join them, the quantity which I get is denoted as V omega. This is known as whirl component of velocity, and again this can be divided into two parts. Maybe if I use another color, that will be better. So, this I can call as V omega 1 and then this I can call as V omega 2. And similarly, I can have V a 2 and V a 1. So, V a 2 or V a in general, that is axial velocity or axial component of velocity. So, V a 1 is the axial component of velocity at the inlet and V a 2 is the axial component of velocity at the outlet or exit. So, this axial component of velocity, if we imagine the turbine, steam turbine. So, there is a turbine shaft, the shaft axis is the axial direction and this component of velocity is acting in the, or it is in the direction of the axis of the shaft. And whirl component of velocity, that is tangential to the shaft or to the shaft axis. So, if we try to imagine the turbine, then these are the physical direction of these two component of velocity, that is whirl component of velocity and axial component of velocity. Now, see, the geometry is basically there are two triangles. So, we can use the laws of basic laws of geometry, and we can get the relationship between different component of velocity. We can do this in a minute, and let us see what type of relationship we will get. Well, in this diagram, I like to make a small change. Generally, this is a difference. So, we want to put it delta VW, or the difference between V omega 1 and V omega 2. Let us see how we get these quantities. Let us see V omega 1. What is V omega 1? If we see this V omega 1, V omega 1 is nothing but, if we see V 1 and if we project it on this plane, then we get V omega 1, and this angle is alpha. So, V omega 1 will be V 1 cos of alpha. Now, let us determine V omega 2. What is V omega 2? So, if we see this is V 2, and let us say this angle, let us call it any name, let us say it is Z. So, if we take V 2 cos Z, then we get V omega 2. V 2 cos Z, if we write, this is V 2 cos of Z, V 2 cos Z, then we can write V 2 cos of, from this relationship 180 degree minus delta, cos 180 degree minus delta. So, what we will get? Minus V 2 cos of delta, minus V 2 cos of delta. So, the magnitude of V omega 2 will be V 2 cos delta. All right. The magnitude will be V 2 cos delta, and then what we can get, delta V omega is equal to V omega 1 plus of magnitude wise it will be plus V omega 2, and then we can write it will be V 1 cos of alpha, then minus of minus V 2 cos of alpha. According to this diagram, according to the diagram which I have drawn, it is like this we can get. So, basically again we can put that V 1 cos of alpha plus V 2 cos of, sorry, this is delta, cos of delta. So, here I like to just tell you that I have used a particular, or we have drawn a particular diagram where delta is an obtuse angle. It need not be an obtuse angle always, delta need not be an obtuse angle always. The value of delta depends on the value of the relative velocity, the blade velocity, and of course, the blade angle, outlet blade angle. So, in some cases it can be an acute angle, or in some cases it can be 90 degree also. But this relationship we can use always, irrespective of the magnitude of delta, we can use this relationship always. So, basically delta V omega is equal to V1 cos alpha plus V2 cos delta, the way I have drawn the delta. If we draw or if we denote delta in the same manner, then we can use this relationship. Now, we can determine also the inlet blade angle. The inlet blade angle if we see, inlet blade angle is given by beta 1, and we can get a relationship like this: tan beta 1 is equal to, how we can get, this is V1 sin alpha, V1 sin alpha is this one, and then V1 cos alpha is this length minus Vb. So, we can write V1 sin of alpha, V1 cos of alpha minus Vb. So, inlet blade angle, if I have to determine, what I have to know? I have to know the velocity or absolute velocity with which the steam is coming out of the nozzle. Well, how do I determine that absolute velocity of steam coming out of the nozzle? This I have told earlier. We have to know what is the incoming enthalpy, what is the enthalpy with which steam is entering the nozzle, and what is the enthalpy with which steam is coming out of the nozzle. So, when we have done the nozzle analysis in the previous class, I have discussed this. So, from there I will get V1, and then nozzle angle should be known to me, and then Vb, the blade velocity or blade velocity due to rotation of the disc, that should be known to me. Why it is important to determine tan beta 1 or beta 1? Because the blading should be designed in such a way, so that the steam enters the blading tangentially without any shock or collision. If there is any shock or collision, if the tan beta 1 is something different from the blade inlet angle, then when the steam is entering, it will make some sort of collision with the blading or with the edge of the blade, and some of the momentum will get lost. All right. So, that we do not want. We want the steam to smoothly glide when it is entering the blading. So, that is why it is important to know, and we can see that the inlet angle for shockless entry, this is called shockless entry, that is a function of the absolute steam velocity, nozzle angle, and the blade velocity. Then we define another quantity. We define a quantity Kb. This Kb is defined as Vr2 divided by Vr1. This is the relative velocity of steam at the blade exit, and this is the relative velocity of steam at blade inlet. This Kb, it is conventionally known as blade friction factor. The concept is like this. The blade is something like this. Okay, let me draw the blade here. This is one impulse blading. The steam is entering something like this. It is moving along the blade surface and coming out of this blade. Now, this is a cross section of the blade. Steam is entering like this, it is a horizontal plane and steam is going out like this. Now, if steam is entering like this and going out like this, and I have told in impulse blading there is no change in pressure. So, the pressure is not changing, the height at which the steam is entering, almost at the same height it is going out. Okay. So, there is no change in pressure, there is no change in the static head. So, the velocity at the inlet and outlet can be different only if there is frictional dissipation, otherwise there will not be any change in velocity. Or in other words, the relative velocity here Vr1 will be equal to Vr2 if there is no friction in the blade passage or the blade passage is smooth. If there is friction in the blade passage, then Vr1 is not equal to Vr2. In general, there can be some friction. So, that is why we define a factor Kb, which is Vr2 Vr2 divided by Vr1. If this is 1, then there is no friction and inlet relative velocity is equal to the relative velocity at the exit. If there is friction, then the relative velocity at the inlet and exit are different. From here, we can also determine what is the frictional dissipation. The frictional dissipation, the kinetic energy which will be lost due to friction, that is equal to half Vr1 square minus Vr2 square. Vr1 square minus Vr2 square. This is per unit mass flow of steam. Okay. So, let me write loss in kinetic energy due to friction. Due to friction, this will be the loss in kinetic energy. Well, once we have introduced this Kb, what we can do? We can write delta V omega. This is a vector quantity, it has got a direction. So, this quantity can be written like this: V1 cos of alpha minus Vb. So, all are vector quantities, these velocities 1 minus k 1 plus Kb. This we can write 1 plus Kb. Now, this needs little bit of derivation, but that derivation is easy and I am leaving this derivation to you. That means, if you try with the velocity triangle, with the combined velocity triangle diagram. So, what one has to do, this V1 one has to change it to Vr1 and V2 to Vr2, and then one can introduce the relationship between Vr1 and Vr2, Vr1 and Vr2 bringing this kb, and then one can get this relationship. So, this I am leaving to you, this derivation you can do easily. Then comes the important parameters. Next, we want to determine what is the tangential thrust. Tangential thrust, this is generally thrust, it is nothing but a momentum, and it is denoted by P. As it is in the tangential direction, we call it Pt, P subscript T, and this P subscript T, this is change of momentum in the tangential direction. So, change of momentum in the tangential direction means, again let us go back to this basic diagram. Here steam is entering with a velocity v1, it will have a component in the tangential direction, this is the tangential direction. So, v1 into cos of alpha in this direction. Similarly, when it will go out, it will have a component in the tangential direction, and if we take the difference between them, then we will see what is the change in velocity along the tangential direction. That multiplied by the mass flow, that will give you the momentum or change of momentum in the tangential direction. So, we will have Pt, that is omega s into delta v omega. This is a vector quantity. Omega s is the steam flow rate. So, this is the thrust which is responsible for doing the work. From the turbine we get the mechanical work or we get the external work. See, this thrust, tangential thrust, is responsible for that. This thrust is responsible for the movement of the turbine. So, that is why this is very important and we can determine it. So, we have to determine the delta Vw or V omega, and V omega I have given two formula like this formula, and initially I have given another formula in terms of V1 and V2. So, either of these we can use and we can determine the tangential thrust. Then comes the axial thrust. Axial thrust again in the direction of axis. If we see what is the change of velocity, we can determine. So, in the direction of axis, in one direction we have got VA1, in another, sorry, at the inlet we have got VA1, that is in the direction of axis, and in the exit we have got VA2. So, we can write P axial is equal to omega s delta V A. Delta V A is equal to V A1 minus V A2, and again V A1 we can write V1 V1 sine of alpha, this is V1 sine of alpha, you can write minus, this is V2 sine of z, that means sine of 180 degree minus delta. So, that is V2 sin delta. So, this is how we can get the axial thrust. Now, axial thrust does not do the useful work, rather it is not desirable to have a very large axial thrust, though we cannot avoid it, there will be some amount of axial thrust, and that is taken care of by thrust bearing, by bearings in a turbine shaft. Okay. So, this is the axial thrust. So, tangential and axial thrust we could determine. Then next we can determine the blading work or diagram work. This blading work or diagram work, we know that the useful component of force which is doing the work, that is PT. So, PT, due to this force there is a movement in the direction of VB, or there is a rotation of the blade. Rotation of the blade, and in the same direction we have got the tangential velocity VB. So, using these two we can determine the blading work. Let us say we call it WD, diagram work, that is why it is called WD, that is equal to PT into VB. So, that means we will have, this is the steam flow rate into delta V omega into V. So, this will be the blading work or diagram work. So, this is the amount of energy which is coming out as external work or as the useful work out of a turbine. Then what is the energy being supplied to the turbine? The energy that is being supplied to the turbine, if we consider only the blade, if we do not consider the nozzle, but if we consider only the blade, then then energy going to the blade passage that will be equal to, let us say, E blade, that is equal to half into omega s into V1 square, that is the kinetic energy. All right. Now, with this we can define the blade efficiency or stage efficiency, or sometimes it is called diagram efficiency. So, let us go to another page. One can define the efficiency of conversion energy conversion eta d, again sometimes it is called diagram efficiency. So, that is why I have denoted it as eta d. So, what it will be? We will have omega s V omega to V b divided by half omega s V 1 square. Now, omega s can be cancelled from both the sides. So, basically you will get twice delta V omega V b divided by V 1 square. Now, you see, if we go back to the initial diagram which we have drawn, or maybe we can go to the first diagram. So, here what we can see in this diagram, that steam is supplied at certain pressure, let us say at certain enthalpy, and then there is a nozzle and then there is a blade. So, in the nozzle there is change in pressure. So, basically there is loss in pressure or drop in pressure and velocity is increasing. And then when the steam is passing through the blade passage, then there is a drop in velocity. So, basically there are number of conversion, and how much will be the inlet velocity and outlet velocity, that depends on nozzle design and blade design. At this point, I mean, a very logical question will arise that are these values arbitrary? Can we choose these values arbitrarily, or is there some sort of a guideline we should follow, so that we can get maximum out of this design? So, if we go to the next diagram. So, here we can see how the different component of velocities are changing from inlet to outlet. Now, you see quite a few things can be selected, like one can select the nozzle angle, one can select the tangential component of velocity for the blade, which is V b. How? Because we know that it is a function of rotational speed RPM and the diameter of the turbine. Okay. One can select that. Or if we see from the other perspective, let us say the power generated, that is torque into RPM. So, we have got some sort of independence of selecting torque and RPM separately, so that we get a product, that is torque into RPM or power. So, if power is also remains constant, one has some independence of selecting torque and RPM. Now, the question is how these design parameters can be selected, so that we get maximum efficiency out of our design turbine. So, probably at this point we are in a position to decide that at least partially. Here you see that we are getting two velocity component, one is V 1 and another is V b. Apparently these two can be selected independently, but let us see whether there is some sort of a relationship or not. So, what we can do, let us define a ratio rho, that is V b by V 1. Again here we have to remember that V 1, that is the velocity at the nozzle outlet, and that depends how much enthalpy drop we are going to allow in a nozzle. Then let us see how Vb depends on V1. If I define this as rho and we call it velocity ratio, then one can show eta d is equal to twice rho square cos of alpha by rho minus 1 plus Kb. Kb, that friction ratio or blade friction factor, we have already got it. So, now one can do a little bit analysis like d eta d by d rho, that should be equal to 0 for maximum efficiency. For maximum efficiency, this quantity should be made equal to 0. So, just let me write it once again. Eta d is equal to twice rho square cos of alpha by rho minus 1, and this is 1 plus Kb. D eta d by d rho, that is equal to, how much will be this quantity? So, if we break it, 1 plus Kb, that is a constant term, then we will have rho will cancel. So, we will have 2 rho cos of alpha minus 2 rho square. Okay. So, this is equal to 1 plus Kb and 2 cos alpha minus 4 rho, and for maximum efficiency this is equal to 0. So, for maximum efficiency, for eta d max, we will have twice cos of alpha is equal to 4 rho, or rho is equal to cos of alpha by 2. So, we can see we have defined rho as, or Vb by V1 is equal to cos of alpha by 2. So, we can see that if we want to run the turbine at maximum efficiency, then we cannot arbitrarily select Vb. I told that V1 comes from how we are, how much enthalpy drop we are going to allow in the nozzle, from there V1 comes. So, if V1 we select arbitrarily, or if V1 is selected independently, then Vb bears a relationship with it for maximum efficiency, and this is the relationship. So, if we put that, we will get eta d is equal to rho is equal to cos alpha by 2. So, twice cos square alpha by 4, then cos of alpha, this is cos alpha by 2. So, cos of alpha by 2 means this is 2 minus 1 and 1 plus Kb. So, we will get cos alpha will cancel, 2 minus 1 is 1, and here it is cos square alpha by 2 1 plus kb. Now, if the blade is assumed to be more or less smooth, then kb is equal to 1. kb is 1 for smooth blade. And in that case, eta d is equal to cos square alpha. So, this will be the efficiency of the blade passage or optimum efficiency of the blade passage. Now, let us go back to the diagram. So, you see that efficiency of the blade passage, that depends on the nozzle angle. So, that is what I told at the beginning, that there are number of parameters. At the beginning it appears that they are independent of each other. We can select them bit arbitrarily, but it is not so. We can see that the blade angle is I mean, it determines what will be the efficiency of the turbine. So, from here again it is interesting to see that eta d, that will have a high value if cos alpha is high, all right, if cos alpha, the value of cos alpha is high. Now, cos alpha, if cos alpha value has to be high, then this angle has to be very small. Okay. This angle has to be very small, but we cannot make it very small due to the mechanical construction. We cannot make it very small, it will be very slant then, and then the blade passage will be very obscured. We cannot do it, there are some limitations. So, generally this angle is kept 12 degree, 14 degree like that. We generally do not go smaller angle than this 12 degree or 14 degree, 16 degree like this. So, these are the typical values of the nozzle for the impulse turbine. Now, this analysis is the basic analysis and it is applicable for impulse staging. Now, we will see what are the different ways of compounding impulse turbine, and that we will do in the next class.